So in section 9.4, we're going to work with multiplying radicals and rationalizing denominators. It starts with two ideas that we've used before, although we're going to use them mostly in this direction this time. That is, the product of two radicals can be written as the radical of the product. Likewise, we can break up the division of two numbers underneath the radical as the quotient of the radicals. We're going to use that more when we start rationalizing denominators. Let's start with problem number 44. Square root of 11 squared. Now I'm going to look at this one a couple ways. And of course, if you can simplify this instantly in your head, then that's fine. This is not one that I would expect you to actually write out a whole lot of numbers, a lot of work for. But square root of 11 squared, well, when I square something, I'm multiplying it by itself. So it's square root of 11 times square root of 11. 11 times 11 is 121. What's the square root of 121? 11. Now, a lot of us probably could have spotted that right away. You could have said, well, square and a square root cancel each other out. They're what we're going to call later inverse operations. So if you can see it that way, that's fine too. Let's look at it one last way. Suppose I'm lazy and I'm like, I don't want to multiply 11 times 11. That's just too big of a number. Let me write it as a square root of 11 squared. This is also hinting at the same thing that we got earlier, that the square and the square root are inverse operations. Square root of the square is just going to be 11. But this idea here, when you have a perfect square underneath the radical, underneath the square root, it's going to simplify very nicely. We're going to use that a lot in this section. So it doesn't hurt to look at it a couple different ways. But for practical purposes, nothing wrong with just saying, oh, well, that's 11. Let's take a look at a slightly different one. Problem number 48. 2 times the square root of 5 squared. Now, much like the previous one, when you're squaring something, that means you multiply it by itself. Where you have to be careful here is that the 2 doesn't multiply anything under the radical. 2 is on the outside, so it stays on the outside. Now, if it helps, maybe I can rearrange this a little bit like this. All I did was I switched the order in which those are multiplied because multiplication is commutative. You can change the order. So let's see here. That'd be 4 times the square root of 25. What's 4 times the square root of 25 going to give me? 4 times 5, which would be 20. Let's check that out. Let's compare 20 to what I would get if I took 2 square roots of 5 and squared it. Let's see if I get the same thing. So, again, you can check yourself using your calculators. Put this in parentheses, 2 square root of 5. Oops. And then hit the squared key. I should get an even 20. Nice. Nothing wrong with checking yourself as you work through your exams or even just your problems at home. How are we looking on 48? Let's try 46 then. Cube root of 9 cubed. Any predictions here? How's this one going to simplify? 9? Yeah, 9. How would you show it? How would you show to one of your friends who knows, some algebra that this is 9? There's a couple ways that I can think of, but what would you do? Anyone? Amanda? Yeah, but how would you show that you can cancel out the 3's? Let me help you out. What would this be if I wrote it using rational exponents? I mean, hope by Wednesday you can write them with rational exponents. What is this using 9 to what power? Inside the radical, or inside the parentheses here. One more time. 9 to what power? 1/3. Remember the boot method? It's kind of the reverse boot. So the 1 comes up, the 3 comes over. 9 to the 1/3. What's 3 times 1/3? 1. We'll take an early break so you can get some 5-hour energy, okay? So yeah, that's one way to show it. Now, I think the way the book would think that you might show it, at least at this point, is if you had something cubed, then you're multiplying it by itself 3 times. So I can bring that together as this. The cube root of 9 times 9 times 9. Cube root of 729 is 9. So that's yet another way to do this one. Or the cube root of 9 cubed, again, is 9. So several different ways you could approach this one. Excuse me. I am a little bit concerned that I got a lot of blank stares when we did this. We did cover rational exponents, and I hope you're really comfortable going back and forth between these two. If not, please get some help between now and, I don't know, Wednesday, right? Okay, let's keep going then. Let's take a look at problem number 16. Square root of 5 times the square root of 15. Well, not much we can do here other than maybe bring these things together underneath the same radical. 5 times 15. In fact, I think there's a shop here in Royal Oak called 515, just down the road a little bit on Washington. Anyways, 5 times 15 is 75. Am I done? Just leave it as square root of 75? No. I think we worked with square root of 75 earlier today. We can break that up into 2 radicals. What times what? 25 and 3. Good. So 25 and 3 leaves me with 5 times the square root of 3. And again, if you want, you can compare your answers numerically. You can compare this with this. They should give you the same numeric answer. I'm guessing about 8.6 or something like that. All right. Let's try some more here. Problem 28. 2 square roots of 7 times 3 minus the square root of 7. Now you have to be a little bit careful on a problem like this. This whole term on the outside, and they don't put parentheses there for you, those are mine, is going to have to multiply each of the terms on the inside. So I'll write it out with a little more detail than maybe you need, and maybe you don't need to write so much detail. That's fine. But I get 2 square roots of 7 times the first term, which is a 3, minus 2 square roots of 7 times the square root of 7. Now let's be careful here. Which one of these terms is the 3 going to multiply? The 7 or the 2? The 2. Because the 3 is on the outside of the radical, so it's not going to multiply what's underneath the radical. So I'll get 6 square roots of 7 minus 2 square roots of 49. Or you could write 7 squared. That works too. We should simplify this a little bit more. What happens with this term? All right, good. 2 times 7. I'll write it all out. 2 times 7. And there is one last thing that I would probably ask, and that is you multiply 2 times 7 and get 14. But that's it. Because we can. It's simpler to write 14, I would think, than leaving around 2 times 7. Can I subtract these? Can I get like 8 square roots of 7? No. These aren't like terms. Yeah, thanks, Kara. These aren't like terms. So that's it. This is as far as you can go is this right here. I mean, if you're really dying to do something on this one, I suppose you could factor out a 2. 2 is the greatest common factor. 3 square roots of 7 minus 7. All right, but I'm not looking for that. I'd be very happy if you get down to here. Well, right here, what we did was we changed square root of 49 into a 7. So you had 2 times the square root of 49 is the same thing as 2 times the square root of 7. Anything else on 28? Let's try number 30. In fact, why don't you try number 30? So minus square root of 3 times square root of 7 minus square root of 15. Oops. So again, you have to distribute. One thing you have to be careful about is distributing the negative sign as well as distributing the square root of 3. That negative sign stays on the outside. Don't bring it underneath the radical. Try and simplify your answers a little bit. One of these will simplify. That's right, but it's not going to allow you to finish simplifying. Okay. This should be a 5 here. A negative times negative would be what? it's just not going to give you, or you do 3 times 7 on the calculator, or you square 3 times 4. But it's just not going to show you square root of 21. It's going to give you a decimal answer. All right. I'll hit the next. I'll hit the left side of class next time I do one of these. Okay, so on the outside, the negative multiplies what's understood to be here a positive. So negative times a positive is negative. 3 times 7 is 21, so I get minus the square root of 21. Likewise, a negative times a negative is a positive. And 3 times 15 is 45. Now, it's true that those aren't like terms, but we can still go a little bit farther with the second of these. What perfect square divides 45? Good. 9 goes in there 5 times, so you should end up with minus the square root of 21 plus 3 square roots of 5. How do we do on that one? Get that one right? Okay. Good. Let's try another one like that. In fact, this is a good one. I would star this one. Might not be this one in particular, but I wouldn't be surprised to see something like this at all. And you'll see this is kind of like a theme throughout the course. You'll end up having to square binomials in one form or another. Square them when you have complex numbers. Square them when you have irrational numbers like this. And the reason I do this is because I want to make sure that when you go into the next class, you don't embarrass me by squaring this out and going, oh, well, that's 9 squared minus 11. All right, that is squaring both of those. You can't. That's not the way it works. What you have to do on this one is rewrite it as 9 minus the square root of 11 times itself. What operation is going to take place from here? FOIL. Is there any hockey fans out there? Yes. Okay. There's an old movie called Slapshot. And the 3 goons in there are like, yeah, the FOIL coach puts them on for every game. So, it's a great movie. I probably. Except, isn't he a Blackhawks fan, though? No, he's a Red. Oh, you're the Blackhawks fan. I'm the Blackhawks. Oh, okay. All right. Anyways, so we have to FOIL this one out. 9 times 9 is 81 minus, now when you do the outsides, what is this 9 going to multiply? Kind of that minus out front. It's going to be minus 9 times the square root of 11. Then you get that inside term yet again. So inside term, minus square root of 11 times 9, well, you're going to get that same term twice. That's always going to happen when you multiply a binomial by itself. So you're going to get the middle term twice. How about the last term? What's the last term going to look like? Mark? Perfect. So negative times a negative is positive. Square root of 121 is 11, as Mark said. So 81. Now, how about these middle 2 terms? Minus 9 square roots of 11, minus 9 square roots of 11. What could I do with those? Yeah, minus 18 of them. Minus 18 square roots of 11. I would ask that you add 81 and 11, but as a courtesy, I'll allow you to use your calculator on that one if you need. All right. Guys, go get some 5-hour energy. I'm trying to mess with you a little bit. All right. 92 minus 18 square roots of 11. If you compare these on a calculator, their decimal values should be the same. So 9 minus the square root of 11 squared, and 92 minus 18 square roots of 11. identical. So on the test, I will not accept this as an answer, but it's good to double check your work. I mean, there's nothing wrong. You can know that you got these things right before you hand in the exam. Nice. Okay. Anything else on 52? Looking all right on that one? And you're going to be ready for one like that come Wednesday. Should I put one on the exam, right? Okay. Let's move into... do you want one more like this to practice, or are you good on this one? Yeah? All right. Let me take a look here in the book, see if they have one like that. If not, we can just give you one. Let me give you something similar this way. Let's do 7a minus the square root of 6 squared. So a little bit, just a tiny bit more challenging. I'll walk around. So this timeout thing here is so that if you're watching the video at home, that you can fast forward it until I get rid of the timeout sign. Okay, looking good. So, as with the last one, start by repeating the binomial. Oops. 7a minus square root of 6. And then FOIL that one. So 7 times 7 is 49. A times a is a squared. Outside terms give me 7a times the negative 1, basically negative 7a times the square root of 6. And the inside terms give you the same thing yet again. The last terms give you a positive square root of 36. If you just want to right away write that as square root of, or write it as 6, that's fine too. The only thing I can do now is combine like terms in the middle. 49a squared minus 14a square roots of 6 plus 6. Got that one? Cool. Oh, if yeah, if this was a multiplication here, then yeah, you wouldn't have to FOIL. There would be no FOIL because this is just one term. So it'd be 7 square roots of a, 7a square roots of 6 times 7a squared roots of 6, it'd be a much different answer. You get 49a squared times the square root of 36. So that's going to simplify to 49a squared times 6, which is 294a squared. So yeah, great point. It's a much, much different problem. Mark and Bailey? Oh, you.
I was just kind of wondering, like, to simplify it further, could you do, like,
Here?
49a squared? Couldn't you just put it as, like, 7a?
You could write it as 7a quantity squared, but I'm not going to be asking for you to write it like that. I'm happy to have it as 7 or as 49a squared.
I was going to ask if you could simplify the square root of 6 down to like the square root of 3.
Well, you can, but neither of these is a perfect square. So we can't really go any further. So it's a good question.
So you just want the 49a squared minus 14a.
Yeah, this is what I'd be looking for the answer to my example, is this right here. Okay, you don't have to. In fact, there's nothing much that we can do with the rest of this. So, yeah, I'd be really happy right there. All right, good questions. Last thing to pick up then is rationalizing denominators. So, we'll start with problem number 56, my guess. Yeah, 56. So, rationalizing denominators. So, problem 56 gives you the square root of 5 over 3. Well, in terms of working with fractions, mathematicians have a lot of rules. Not just fractions, I should say, working with radicals, mathematicians have a lot of rules in terms of what constitutes a simplified form of a radical. And if you look back on page 755, and I'm sure everybody's read 755, not, but that's okay. It says all this stuff in mathematics ease that deserves some translation. So it says each factor in the radicand is to a power that is less than the index of the radical. All right, translation means no perfect squares underneath the square root. Simple. No cubes underneath the cube root. So the stuff we were doing in the last section, where we split up the square root of 75 as the square root of 25 times the square root of 3, that's getting rid of the perfect square underneath the square root. That's what they want here. Then they hit you with the radicand contains no fractions or negative numbers, and no radicals appear in the denominator of a fraction. This is the one that's going to kind of catch us here. We don't want radicals in the denominator of a fraction. So when you look at a problem like 56, the first thing you see is, oh, we got a fraction. Oh, well, we can't have fractions, so I'll rewrite that as a square root of the square root of 5 over the square root of 3. And you're like, ha, cool, I got rid of the fraction underneath radical. But then they catch you with the third rule. No radicals in the denominator. And it's at this point we've got to think a little bit. Square root of 5 over square root of 3 is just an expression. It's a ratio of two radicals, etc. We can't multiply both sides of our equation to get rid of the radical because there are no both sides of the equation. You're just trying to simplify an expression. And when you're trying to simplify an expression, your choices are kind of limited. But I can multiply by 1. So the question is, what form of 1 can I choose to make a meaningful simplification? Well, I could choose to multiply by the square root of 3 over the square root of 3. How does that help? Good. You get the square root of 15 over the square root of 9. But what happens to the square root of 9? It's 3. It helps because what I end up with here is a perfect square in the denominator. And then I can simplify that. As before, you can check that these two things are the same. You can check that the square root, just a bad recording day altogether. Out of focus, screen's flashing off. Let's check the square root of 5/3 and compare that to the square root of 15 over 3. Identical. And again, I'm encouraging folks, I really want you to double check these on your exam to know that you got them right. Yes, sir.
Can you multiply by 1 before you take it out from under?
Well, the multiply by 1 is effectively right here. When I multiply by square root of 3 over square root of 3, something divided by itself is 1. So,
No, I know that, but I'm saying can you do it before you put
oh,
divided
oh, yeah, sure. So right here, say square root of 5/3 and do 3 over 3 and get square root of 15 over 9. Sure. Yeah, it works out to the same thing. I see what you're saying. That it? Let's try another one like that. Problem number 58. Square root of 8 over 7. Let me give you two of these to try. And problem number 60. 8 over the square root of 10. I'm going to kind of walk around and try and help out a little bit. Help each other out too, because I can't always make it around to everybody at once. But see if you can't make it around or just make it through both of these. Problem 60 is going to need a little extra step of simplification when you're all done. That's okay. this doesn't multiply by the side.
Want me to calculate?
Okay, so for the first one, now I'm not sure. Are you a fan of breaking it up? I mean, that's my habit always, is to break it up, square root of 8 over square root of 7, and then multiply by root 7 over root 7. I get the square root of 56 over the square root of 49, and at least the square root of 49 will simplify as 7. So what makes this work is that essentially you're multiplying by 1, something over itself. So that's not going to change the value of the expression, it's just going to change the way it looks. Likewise, in problem number 60, I can multiply by the square root of 10 over the square root of 10. I get 8 square roots of 10 over the square root of 100, which is 8 square roots of 10 over 10. And I think I gave you a little bit of hint that there's going to be a little extra simplification here. 2 goes into 8 4 times and into 10 5 times, so you should end up with 4 square roots of 10 over 5. Now here's a good question. Can I cancel the 5 into the 10? No. You can't cancel from outside the radical to inside the radical. That's it. That's as far as we can go with that one. Oh, yeah. Very good. Very good. We can go a little bit farther here with square root of 56 because 4 divides into 56 evenly. So let's see. That's going to go in what? 14 times? Square root of 4 times square root of 14 over 7. So it's going to be 2 square roots of 14 over 7. Yeah, thanks. Now, a better way is probably what you suggested originally. That is to break up the square root of 8 as square root of 4 times square root of 2. So let's take a look back at it that way. Square root of 8 is square root of 4 over square root of 2 over square root of 7. And you get 2 square roots of 2 over the square root of 7. You still have that square root of 2 problem to deal, or square root of 7 problem to deal with in the denominator. So multiply by root 7 over root 7 and get 2 square roots of 14 over the square root of 49, which is 7. Nice. Thank you. Let's continue rationalizing denominators, and we'll work with problem number 76 next. (11) over the square root of 75 s to the fifth. They should make a law that makes it illegal to put 5's and s's in the same problem. Alright, so what I would suggest is that before we start rationalizing, don't multiply by root 75 s to the fifth over root 75 s to the fifth. That's a really long way to do this problem. Let's see if we can't simplify the denominator first. In fact, we've worked with 75 several times today. How can we break up 75? 25 and 3. But did you catch what we did with that odd power of a variable underneath the radical? S to the fifth. I can break that up into 2 pieces. One's a perfect square, one's not. What's the perfect square part? S to the fourth and an S. So you just split off that extra one there. Now it's going to work out pretty nice. What's the square root of that first term? 5s squared. Square root of 3s. So a lot simpler of a radical to deal with in the denominator. We still have to get rid of it from the denominator, but I think I'm going to be much happier doing it here as opposed to doing it here. What should I multiply this by to get rid of the radical? Square root of 3s over square root of 3s. Thank you. And when we do that, we get 11 square roots of 3s over 5s squared. 3 times 3 is 9. S times s is s squared. There's a little bit more work to do in the denominator. See if you can't anticipate me. Square root of 9s squared, Lisa? 3s, thank you. 3s, good. And last but not least, 3s times s squared, 15s to the third. Okay, not so bad there, not so bad. But I think it made it a lot friendlier of a problem to simplify the radical first as opposed to trying to multiply both numerator and denominator by the square root of 75 s to the fifth. That would have been a real pain. Okay, let me give you kind of a practice problem that probably could have been in the last section before we move on into this section. Move on to the last part of the work in this section. So that would be, let's do square root of 11 minus square root of 7 times square root of 11 plus the square root of 7. So a good one to practice foiling out two binomial expressions. See what you should get. You should get a remarkably simple result. A nice friendly result. But give that one a shot. See what you can come up with. Yeah, it's an example problem. It's not one that's really in the book, but you know, a lot of times, like a good author, I'll do a little foreshadowing. This is some foreshadowing of some stuff that we're going to do in a little bit. Square root of 11 times square root of 11 is the square root of 121. Plus the square root of 77 minus the square root of 77 minus the square root of 49. So The important part to see is what happens when you simplify the middle terms. They cancel each other out. You're left with 11 minus 7, which is 4. Yay. Simplified pretty nicely, didn't it? That's always going to happen when you have something of the form a minus b times a plus b. You're going to get a squared plus ab minus b squared. In fact, you're going to see a familiar factorization. Factorization is the difference of squares. So it's nice when you're multiplying those, you get those middle terms to cancel each other out. And you end up squaring the end terms, taking their difference. So what's that have to do with anything? Well, we'll find out. What we're going to finish up with in this section is rationalizing denominators as of the form problem number 94. So we've got 3 over the square root of x minus 2, which leaves us with this ugly radical term in the denominator. Well, we mentioned earlier that we don't want to divide by a radical. So we need to multiply by something to get rid of that. One choice would be to multiply by the square root of x over the square root of x. And that'll get rid of that there, but then I'll end up with 2 square roots of x here. So multiplying by root x over itself doesn't work. I need a bigger, bolder idea. Any ideas? What could I multiply by to help get rid of... Oops. That's... You know, that looks like it's underneath the whole thing. It shouldn't be. So let me just rewrite it down here. 3 over the square root of x minus 2. Any suggestions, Rhonda? Square root of x plus 2. So what you're going to do is you're going to change the sign from minus to plus or plus to minus, depending on what you have. You're going to multiply effectively by what's called the conjugate. It's a binomial with the same terms, just a different sign between those two terms. So the idea here is that this should help get rid of the radicals in the denominator. In the numerator, I just get 3 square roots of x plus 6. How's it going to look in the denominator when I FOIL this out? Well, we'll get some cancellation. I get square root of x squared. What would the outside terms be? Plus 2 square roots of x. Inside terms would be minus 2 square roots of x, and then minus 4. Now there's something nice that happens here. What is it? Those cancel. The denominators cancel. In fact, I get some more simplification in the denominator. What is it? What else simplifies in the denominator? Good. You get an x. So we're left with x minus 4 in the denominator. But as advertised, got rid of the radicals in the denominator. Let's try another one or two like that to close out the section. Is there a question on that one, Bailey? Square root of x squared just became the x. All right, so another one like that would be, well, let me give you this example. Square root of 2 over square root of 7 plus the square root of 5. This one should have some nice simplification. What should I multiply by in this one? Olivia? What can I multiply by here? Amila? Maybe some help?
Square root of 7 minus square root of 5.
Good. Square root of 7 minus square root of 5 over itself. And in the numerator, let's distribute that square root of 2. In the denominator, you get to FOIL things out. Should get a nice number when you're all said and done in the denominator. So what terms am I going to get here when I FOIL this out? Square root of 49 minus square root of 35. Good. Plus square root of 35 minus square root of 25. These middle terms cancel each other out, which is great because the other two terms are perfect squares. I end up with a 7 here, a 5 here. 7 minus 5 gives me 2. Nice. So, yes.
Do you expect to see that work on the test, or since this
I,
some squares, we can just go straight to the.
I'd like to see something. At the very least, even just writing down, for me, writing down this right here, you'll probably get 1 point. If that's all you did, if you just stopped right here, I'd be so happy that, oh, at least you understood something. You probably get a point right there. I probably would like to see some work. The exact work you show is up to you. You do have to be a little bit careful because this pattern of this canceling out only works when you're multiplying the difference of squares. Okay, so where's an example of something that's not the difference of squares? We'll see that in problem number 96. And I kind of leave it up to you as to how you want to solve these things. I know what you're saying, and my only misgiving about that is sometimes people want to use that trick when they multiply any two binomials. And it only works when you're multiplying the conjugates like we just did. Now before I do problem number 96, let me share with you kind of a reminder / example. It's not as a big a deal, but it's just going to save me a step at the end. And that is, when you're working with fractions, you can put the negative in a fraction in several places. You could put it in the numerator, you could put it out in front, or you could put it in the denominator. No matter where you put it, overall the fraction is still negative. So if I want to, for my convenience, I can move a negative from the denominator to the numerator. Or I can move it from the denominator to out in front. Or from out in front to the denominator or numerator, wherever I want. All three of these equal -2. And all I'm saying is that I have a lot of freedom where I put the negative in a fraction. So that's kind of like a little bit of a heads up for some of these. And you know what? I think I just wasted my breath a little bit because we don't quite need it in problem number 96. I was thinking it was a little bit different, but it's all right. 96 is a good example of something I was worried about in general with regard to your question, Mitchell, and that is, yeah, there are shortcuts. What would I want to multiply things by in problem number 96? Square root of 3 plus 2 over square root of 3 plus 2. So this. Now, the shortcut you're taking works great in the denominator. And if you're comfortable doing that, that's fine. But where I get nervous is in telling people that shortcut is because they want to do it here in the numerator. And you can't. It's not going to work in the numerator. So if you show me that shortcut in the test, that's fine. Okay? All right, so see if you can't finish this one up. This is going to be our last one for this section. I think the denominator is going to work out pretty nice. There's not much of a difference in foiling out the numerator and the denominator. But what is different is the signs. So in the denominator, you get a little cancellation. In the numerator, well, you're not going to get cancellation per se. Well, no, you got to keep going. Inside term gives you the square root of 6 again, so we can square root of 6 plus square root of 6 again, and then the last term is the square root of 4. Okay, so a lot going on with this one. We need to carefully FOIL this out. So in the numerator, I get the square root of 9. Outside terms give me plus square root of 6, plus the square root of 6 again, plus the square root of 4, and that's it. Underneath here, I get the square root of 9, and pretty much I'm going to get the same terms. The only thing that's going to be different is the coefficients. Plus the square root of 6, minus the square root of 6, minus times a plus is a minus the square root of 4. Now, there's an important difference between the numerator and denominator. Whereas in the denominator, those square roots cancel, in the numerator they don't. And what I saw a lot of people giving me was the square root of 12. These do not add together to give you the square root of 12. There's no circumstance under which you can add the square root of 6 and square root of 6 and get the square root of 12 or anything like that. These are like terms, though. I've got one of them here and one of them here. 1 plus 1 gives me 2. So I'll end up with 2 square roots of 6, and I'll have a 2 from the square root of 4 and a 3 from the square root of 9. Likewise, I'll have a 3 here minus 2. But the big thing to see here is square root of 6 plus square root of 6 gives me 2 square roots of 6. Let's finish it off. 2 and 3 gives me 5 plus 2 square roots of 6 over 1. Do I need to write divided by 1? No. So I can just write it as 5 plus 2 square roots of 6. And that's my final answer. All right. Doing good on that one. Any thoughts on number 96? Yes?
I got 5 plus 6 square root of 2. Like 6 and 2 or...
Not sure how you would have switched those. The ones are on the outside, so 1 plus 1 gives you 2 of that common term of square root of 6. So, why don't you show me that in a second. And let me give you some homework. We'll take a break. So homework, 15 through 99. But you can skip some problems. Skip 23, 33, 39, and 41. You can also skip 71, 73, and you'll like this one. Skip 79 through 89. I had a pretty good weekend. Yes, thanks. Okay, let's take a break here.